Hi, we're Brianne, Eva, and Hunter, and we are going to look into developing models to predict LDL levels, so hopefully patients can avoid being around needles too often. So why do we want to know about the LDL levels? LDL is low-density lipoprotein. It's also known as the bad cholesterol, since it's the type that can build up in arteries. And when there's a high level of cholesterol, particularly the bad kind, you can have complications like angina, stroke, or heart attack. And these are obviously some very serious complications that could potentially kill the patient or put them on a very long and expensive road to recovery. Globally, high cholesterol complications kill 2.6 million people each year. And right now, the method for detecting LDL levels is through a blood draw, which involves a needle being inserted into a vein to remove blood for testing purposes. This is expensive, and it can also be very traumatic for patients. According to the CDC, healthy adults, meaning they don't have any conditions that could impact cholesterol levels and they don't have a family history of it, they need to get their cholesterol checked every 4 to 6 years. If there's family history of it, then they have to be tested more often. So our goal is to use machine learning to predict LDL cholesterol levels so that we can screen patients so that those who predict as not having high LDL or high cholesterol wouldn't have to get their blood drawn that year and then keep checking as time goes on, because as we do age, our health does change. And then if it does predict as high or borderline, then the patient could go in for some confirmation tests instead of just getting tested for the sake of being tested. And now I will turn it over to Hunter, and he will go into the background of our data and data exploration.
Our data came from the National Health and Nutrition Examination Survey pre-pandemic dataset, which ran from 2017 to March of 2020. We took a demographic, body size measurement, and cholesterol dataset and removed the comment variables from them. Then we joined the prior datasets to the completed observations of the cholesterol data to get our full dataset. Next, we took a look at the distributions of numeric variables by creating histograms of each variable. Here we can see that our target variable, LDL cholesterol, is unimodal, centered around 100 milligrams a deciliter and slightly skewed to the right. Looking at the demographic numeric predictors, we see that age has a multimodal distribution and income ratio is centered around 1 and heavily skewed to the right. The body measure numeric predictors of weight, BMI, arm circumference, waist size, and hip circumference were also skewed in the positive direction. Then we took a look at the categorical predictors class balance. Not surprisingly, the English class made up a large portion of features that focused on language. For other demographic features, we found that there's a balance between male and females, a good amount of observations for each ethnicity, mostly US-born subjects, and a good amount of observations for both education and marital status. So to close out our EDA, we created dummy columns for categorical predictors and found the correlation between all the variables. We noticed that LDL cholesterol did not exhibit a strong correlation between any variables. Language variables exhibited a strong correlation with other dummy variables relating to the same language and a strong negative correlation for variables in another language. The male class showed a strong positive correlation to leg circumference, height, and arm length, while the female class displayed the opposite relationships. Finally, many of our body measurements, such as BMI, arm, hip, and waist circumference, were directly correlated. So to begin our training, we took 80% of the observations from the dummy column dataset for a training dataset. Then we normalized and imputed the training and test data using the 5 nearest neighbors of the training dataset. Next, we set up our resampling data for tuning models using tenfold cross-validation. And finally, we created another smaller dataset that focused on gender and the numeric body measurements in the hopes of getting a more simplistic and interpretable model. So we began modeling with a set of linear regression models, beginning with ordinary least squares regression. We created a model predicting cholesterol using all the variables from the dummy training data. Now, as evidenced by our QQ plot, our model did not have normally distributed residuals, so we were struggling to meet our assumption of normal data. We created another dataset removing the highly correlated variables, and another dataset from that with box-Cox transformations to try to combat this. These datasets ended up being used in the rest of our training. So we trained OLS models with these two data sets and the reduced numeric feature data set from earlier, trying various transformations on cholesterol, but we also kept getting very similar QQ plots. So we ended up going with a final OLS model using the significant features from the reduced correlation dummy data. Now these features included age, height, BMI, leg circumference, arm circumference, birthplace, education, and language. We then trained a variety of models using the dummy dataset without highly correlated variables, the Box-Cox transform dataset, and the reduced numeric dataset. For principal component and partial least squares regression, we evaluated 1 through 32 components for the dummy and Box-Cox dataset and 8 components for the reduced dataset. Then we trained ridge regression models evaluating 15 penalties ranging from 0 to 0.5. And finally, we trained elastic net models with penalties of 0, 0.1, and 0.01 from 5% to 100% of the full solution. Now, when looking at the diagnostic plots, our dummy data and Box-Cox data had nearly identical performance, so we only evaluated the dummy data on the test dataset. And we predicted against the test dataset, the best performing linear model was the ridge regression with a root mean square error of 32.9 milligrams a deciliter. And now I'll pass it along to Brianne to talk more about nonlinear modeling.
Thanks, Hunter. So in total, we explored 5 nonlinear models. This included the support vector machine with radial function, which had the parameters set for scaling and cost. Scaling was explored using the sigest function in R, and cost was explored between 2 to the negative 4 and 2 to the power of positive 4. And the predictors were centered and scaled for pre-processing. The final model had a cost of 0.25 and a sigma of 0.035 and gave an RMSE of 35 milligrams per deciliter using 3,377 support vectors. The support vector machine with the polynomial function used the same cost exploring range and explored degrees between 1 and 3. Ultimately, it picked a cost of 2, a degree of 2, and a scale of 0.001, again to get an RMSE of 35. The next one we explored was the k nearest neighbors, which we only had to look at the k values, so we looked at values from 1 to 40 with the final model using 20, which again gave us an RMSE of 35. Multivariate adaptive regression splines, or MARS, was explored, where we looked at a range of the degree of the parameter addition, which was between 1 and 3, and term retention, or end prune, was looked at between 2 and 38. The final model only kept 1 term, but it still gave us an RMSE of 35. And the neural network, we explored weight or decay at 0, 0.01, and 0.1, as well as size or the number of hidden layers. We looked at 3, 7, 11, and 13. The final model used 13 hidden layers and a weight of 0.1 and gave us the worst RMSE value at 43. Overall, none of the nonlinear regression models did very good, but when we tested them using the best model was the support vector machine model with the radial function, which gave us a test RMSE of 33, while neural network still held on at the worst, but this time at 37 for its test. So the plot on the right is the predicted values in the multicolors, as well as the observed actual values of the test set, which are in black. As you can see, none of these models are really good at predicting extreme values or anything that's not 100 plus or minus about 20 milligram per deciliter values. And I will now turn it over to Eva for some regression trees that we've looked at.
Moving on to regression tree models, a total of 8 different tree models were examined. These models fall into 5 main categories: cart models, of which we examined 2 models based on their different tuning parameters, bagged trees, random forest, boosted trees, and finally, model trees, of which we constructed 3 different models, which were M5, rule-based M5, and cubist. Two different cart-based regression tree models were built. These models were built using two different training methods. Using rpart, this method trained the model based on complexity parameter, or CP. By default, this parameter is set to 0.01. An increase in this parameter reduces tree size, and a decrease in this parameter increases tree size. As the CP parameter decreases, there is a risk of an overfitting the model. However, despite this, we chose to use a CP of 0.003. This resulted in a cart model trained using the rpart method with an RMSE value of 33.0 milligrams per deciliter. Using rpart2, this method trained the cart model using max depth. Looking at the cart-based splits from our model training using complexity parameter tuning, a max depth of 6 was selected. This is in order to reflect the number of splits obtained from the CP parameter tuned model. This resulted in a cart model trained over max depth with an RMSE value of 32.9 milligrams per deciliter. As the max depth tuned model slightly outperformed the complexity parameter tuned model, the max depth model was used for final model comparisons. Our bag tree model was trained using two tuning parameters. The complexity parameter used was 0.003, and this was done to reflect the same complexity parameter used for our cart models. The other tuning parameter used was nbag. This reflects the number of bootstrapped replications that need to be performed. By default, this is set to 25 iterations, an increase in which increases model performance at the cost of computation power. For our testing, this parameter was increased by 5 iterations until no further improvements in RMSE values were seen. And our final tree bag model used a CP value of 0.003 and an nbag value of 70, resulting in an RMSE value of 33.1 milligrams per deciliter. Our random forest model had one main tuning parameter, which were the number of trees. In this model, more trees may produce a better performing model at the risk of overfitting. Our model used an entry value of 300, as it was the least amount of trees to produce an adequate model. This resulted in our model with an RMSE value of 33.1 milligrams per deciliter. Finally, our boosted tree model used stochastic gradient boosting. For this model, bag fraction and train fraction parameters were left at their default values. The number of trees was taken from our random forest model and set at 300 trees. Using a tuning grid, shrinkage of 0.01, and a smaller interaction depth created a model with the lowest RMSE value. Using these parameters, our boosted tree model resulted in RMSE values of 32.9 milligrams per deciliter. Model trees are decision trees with a linear regression model at each of the terminal nodes that predict continuous variables. For our project, we modeled 3 different model trees. Our first 2 models are M5 model trees. The second of these is a rule-based model. For model tuning, both can be tuned over the M value and Weka control. For both, we set the M value of Weka control to 5. The M5 model obtained an RMSE value of 33.6 milligrams per deciliter, and the rule-based M5 model obtained an RMSE value of 32.8 milligrams per deciliter. The last M5 model was the qubits model. For this model, there are 2 available tuning parameters. These parameters are the number of committees and the number of instances. By using the default parameters available, we can see that 0 instances and 10 committees provided the best performing qubits model. The RMSE value of this model was 32.6 milligrams per deciliter. By looking at this summary table, we can evaluate all of the models tested by model type. Overall, the regression tree models outperformed the linear and nonlinear regression models in terms of performance measured by RMSE. Our best performing model was the qubits model with an RMSE value of 32.64 milligrams per deciliter. However, this isn't to say that this is the most optimal solution to the problem that we were looking to solve. As prefaced earlier, our goal with this project was to be able to predict LDL levels to facilitate screening to encourage patients at risk of high LDL levels to seek out their primary healthcare providers. However, with the models obtained from our project, we cannot confidently recommend our optimal qubits model for medical or at-home use. In the plot of our qubits model predictions against our LDL readings, we can see that our model exhibits high bias and performs poorly in trying to predict much variance in LDL levels. Use of our model as it stands runs the risk of misguiding patients of their true cholesterol levels. Thinking of improvements that can be made, the first potential solution to the limitation of our model may rely on acquiring more health data. Some non-invasive health data that could be helpful could be information regarding patient blood pressure, as there is a direct relationship between higher cholesterol and increasing blood pressure. In addition, given some more time, the development of a patient-facing application, possibly in the form of an R-Shiny application, where a patient may input their body measurements and other relevant health data, could be developed to provide patients with immediate information to see if they need to see their healthcare providers for further health checkups. Overall, the traditional method of using blood draws to ascertain LDL levels takes up patient time, and the accompanying lab tests and doctor's visits are a direct cost to patients. By taking the factors that play in predicting cholesterol LDL levels, Perhaps a future idealized model could be adapted into a customer-facing application to provide patients with more information to help them determine their healthcare needs. Thank you for watching our presentation. Here's a list of all of our references for this presentation.